Here, we see how Kirchhoff's first law applies to a fluid node, which is similar to a junction in an electrical circuit. The key idea is that charge behaves like an incompressible flow, meaning it cannot accumulate or disappear at any point. In this example, the current flowing into the node is 5 amps, and it splits into two paths carrying 3 amps and 2 amps respectively. The sum of the currents entering the node equals the sum leaving it, which is the fundamental principle behind the node equations we use in circuit analysis. This ensures that all currents are accounted for and helps maintain balance in the system.
Can you work out the missing current I?
Consider a circular walk on a mountain. The amount of climbing up is balanced by the amount of going down. The elevation rises and falls in a way that the total ascent you make going uphill equals the total descent you experience going back down. When we look at a circular loop in a circuit, the total voltage changes going around the loop always add up to 0. That means the voltage rises, like those provided by batteries, are balanced out exactly by voltage drops, like the ones across resistors. In this example, you can see a 12-volt battery pushing voltage up, and a 6-volt battery also stepping up voltage at a different part of the loop. As the current flows through the resistors, the voltage drops across them bring the total voltage back down. So, the sum of all the voltage increases equals the sum of all the voltage decreases, which means the energy supplied is equal to the energy used within the loop. This principle helps us understand how voltage distributes in any closed circuit.
Think of this diagram like a path that starts and ends at the same point in a circuit loop. When energy is added, such as from a battery or power source, it's like taking a step up in energy level. As the current flows through resistors, energy is used up, which is shown as steps down. The key idea here is that the total energy you put into the loop is exactly balanced by the total energy used or lost as the current moves through the components. This balance is what Kirchhoff's second law tells us. The equation below summarizes this relationship. The sum of all the electromotive forces must equal the sum of all the voltage drops. This concept lets us create loop equations, which are essential tools for analyzing circuits and figuring out how voltages and currents distribute throughout the system. To understand the loop walker's sign convention, imagine a person walking along a circuit. When the walker moves from the negative to the positive terminal of a battery, it's like stepping up, so we assign a positive voltage change. If the walker goes from positive to negative, they're stepping down, which means a negative voltage change. Now, when the walker moves through a resistor in the same direction as the current, it's like riding the current downhill, so the voltage change is negative. But if they're moving against the current, like walking upstream, the voltage change is positive. This way of thinking helps us keep track of voltage changes consistently when analyzing circuits.
Let's look at how physics concepts connect to algebra when solving circuit problems. Kirchhoff's current law, or KCL, helps us identify the variables, like the unknown currents at different nodes in the circuit. Kirchhoff's voltage law, or KVL, focuses on the loops, setting up the structural equations that define the boundaries of the system. Then we have Ohm's law, which acts as a bridge by translating static resistors into dynamic voltage drops. Together, these laws give us a clear map of the circuit's behavior, where physics sets up the problem's layout and algebra helps us find the exact numerical solutions. First, we draw current arrows at the junctions, guessing their directions, since the math will help us correct any mistakes later on. Then, we write the Kirchhoff current law equations for those junctions, making sure the current flow is accounted for properly. Then, we move on to tracing closed loops in the circuit and writing the corresponding Kirchhoff's voltage law equations using the loop walker rules. Finally, we solve these equations simultaneously, either through substitution or using a matrix method, to find the exact values of the variables. This step-by-step approach simplifies the process of analyzing complex circuits. Now let's move on to the masterclass problem. Here, we need to find the exact current flowing through every branch of this circuit. The circuit consists of two voltage sources, one with 12 volts and another with 6 volts, connected through a combination of resistors,
2 ohms, 6 ohms, and 4 ohms. The resistors are arranged in such a way that the 2 ohm resistor and the 6 ohm resistor meet at point A, while the 6 ohm resistor and the 4 ohm resistor meet at point B. To solve this, we can apply Kirchhoff's laws and use systematic methods to determine the current in each segment, ensuring we account for the voltage drops and the polarity of the sources. This will give us a complete understanding of the current distribution across the circuit. Let's start by assigning the currents in this circuit. We assume that both the 12-volt and 6-volt batteries push the charge upward through their branches, meeting at node A and then flowing downward through the middle resistor. This means current I1 moves up from the 12-volt battery through the 2 ohm resistor, current I2 moves up from the 6-volt battery through the 4 ohm resistor, and current I3 flows down through the 6 ohm resistor between nodes A and B. Let's start by assigning the currents in this circuit. We assume that both the 12-volt and 6-volt batteries push the charge upward through their branches, meeting at node A, and then flowing downward through the middle resistor. This means current I1 moves up from the 12-volt battery through the 2 ohm resistor, current I2 moves up from the 6-volt battery through the 4 ohm resistor, and current I3 flows down through the 6 ohm resistor between nodes A and B. If our initial guess about the current direction turns out to be wrong, the algebraic sign of the result will simply be negative, which just means the current flows the opposite way. So we can rely on this approach as a reliable starting point for analyzing the circuit. Now let's focus on the node where the three currents meet. According to Kirchhoff's current law, the sum of currents entering this node must equal the sum of currents leaving it. Here, currents I1 and I2 are flowing into the node, while current I3 is flowing out. This means we can express the relationship as I3 equals I1 plus I2. This simple equation is key to analyzing how current is distributed at this junction and helps us solve for unknown values in the circuit. Now, let's focus on writing the equation for loop 1 using Kirchhoff's voltage law. We start at the bottom left corner and move clockwise around the loop. First, we go up through the 12-volt battery, which adds 12 volts to the sum. Next, the current I1 passes through the 2 ohm resistor, causing a voltage drop of 2 times I1, which we subtract. Then, the current I3 flows through the 6 ohm resistor, producing a voltage drop of 6 times I3, which we also subtract. Adding all these changes together, the total voltage change around the loop should be 0, giving us the equation 12 minus 2 times I1 minus 6 times I3 equals 0. Simplifying this, we get I1 plus 3 times I3 equals 6, which we'll refer to as equation 2. This equation helps us relate the currents in the loop and is a key step towards solving the circuit. Now let's move on to writing the equation for the second loop using Kirchhoff's voltage law. We start at the bottom right corner and move counterclockwise around this loop. First, we go up across the 6-volt battery, which adds 6 volts to our equation. Then we move through the 4 ohm resistor with current I2, which causes a voltage drop of 4 times I2, so we subtract 4 I2. Next, we go through the 6 ohm resistor with current I3, which gives a voltage drop of 6 times I3, so we subtract 6 I3. According to KVL, the sum of these voltages around the loop is 0, so we set the equation as 6 minus 4I2 minus 6I3 equals 0. Rearranging this gives us the second equation, 2I2 plus 3I3 equals 3. This equation will help us solve for the currents in the circuit. Now that we have our system of equations set up, we can substitute the expressions for I1 and I2 into the first equation, which relates I3 to the sum of I1 and I2. By doing this, we simplify the equation to isolate I3. Solving this, we find the value of I3 to be 1.36 amperes. Using this value, we then calculate I1 as 1.91 amperes and I2 as minus 0.55 amperes. These results give us the current values in each branch, with the negative sign in I2 indicating direction opposite to the assumed positive flow.
This completes our solution for the currents in the circuit. Here we see the final setup with current values annotated for each branch. The first branch carries about 1.91 amps upward, while the middle branch carries 1.36 amps downward. Interestingly, the current in the right branch is 0.55 amps flowing downward, which is opposite to what we initially expected. This happens because the 12-volt battery is stronger than the 6-volt battery, pushing current back through that side of the circuit. This is a good reminder that while the physical setup might seem complicated, the mathematical principles guiding it are precise and reliable, so we can trust these results to guide us accurately. If you found this presentation helpful, I encourage you to visit physicsib.com. It offers a structured and interactive course designed to deepen your understanding and support your learning journey in physics. Taking advantage of resources like this can make complex topics more manageable and provide a clear path through the material. Please take a moment to like and subscribe so you don't miss future content. For more detailed and structured courses, you can visit physicsib.com, where there are interactive lessons designed to support your learning. Thank you for watching and being part of this journey.